Howdy and welcome back. So we're going to go through the Iterator Constructor, its implementation, and we're going to assume that its parameterized constructor is going to take a pointer to the root of some sort of binary search tree. So let's go ahead and just kind of decompose the class definition before we get into the actual definition of our binary search tree. Iterator's parameterized constructor. We can see here that binary search tree is being defined as a class template, and we'll have two type parameters, T1 and T2, which resembles that of our node. The name of the type we're creating is a binary search tree iterator. This could have been named differently, but I thought this was descriptive till I realized I probably should have put in been more descriptive to say that it was not only a binary search tree iterator, but one that performs the iteration in order. But we'll go ahead and kind of go with what we've got and continue this on. Notice here we're using that inheritance scheme to essentially say that the type of iterator being implemented is going to be a forward iterator. And this is, again, has to do with traits and other things that we're not necessarily going to get into in this class. However, once we're done with this, we're actually going to be able to, say, pass our binary search tree to a STL algorithm that supports forward iterators. For instance, we'd be able to call STL find on a binary search tree that we've implemented in the previous lesson and whose iterator is being created in this lesson. So that's pretty cool. But again, without this information here, we would not be able to use these iterators with those algorithms. So this is key for that. So we can go ahead and see our parameterized constructor. It's going to take a single argument of type node. Well, it's going to be, a pointer to a node of T1, T2. And we're going to go ahead and name that parameter iter init. That's good. Not much relevance here. Let's continue on. So two private data members. Iter is going to be a pointer to a node, and it's going to kind of preserve where we are. So if we had a tree, iter is going to preserve kind of our state where we currently are. So it's just going to be pointing to the node that we're currently visiting. Now this stack here, I briefly kind of communicated that we're not going to implement our traversal in a recursive manner. And remember, when we implemented the in-order traversal in a previous lesson, we relied on the stack to kind of remember where we were in the process. So remember, we went as far left as we could, and that pushed a bunch of activation records onto the stack. And then once we say we returned from one node, we could get back to the node that got us to the current node by just popping that activation record, and boom, we're back to its parent and could continue on the process. Since we're not implementing a recursive algorithm, what we're going to want to do is preserve the state in the same exact manner. And here, in order to do that, we're going to rely on the stack data structure. So, this is pretty cool. It's essentially going to mirror what would have happened if we were working with a recursive definition of this. Our iterative solution is going to leverage this data structure to provide that kind of history to remember where we've been, so we can step back from the child to its parents, or in this case, whatever might be next in terms of our in-order traversal. So let's go ahead and run through the implementation of this. It's the setup of the constructor is quite easy. It's going to be basically we're passed in some sort of root node, and what do we have to do? We have to get to the first node that is going to present, or that would present in an in-order traversal. So at the end of this, we want our iter data member to point to that element. So let's go ahead and begin looking at this. So our parameter iter init is going to be initialized, in this case, with the root address of the root node. That's how we'd invoke this. We'd go ahead and create a new binary search tree iterator, and we pass in the root of the tree for which these will become an iterator for. We can see here, we go ahead and initialize directly iter with that address. And then we go ahead and jump into the body of this function. So right now, iter is pointing here, assuming the root was passed in. I have a check here. The first thing I'm going to do is going to see whether or not iter was assigned, or in this case, initialized with the null pointer. If so, I'm simply going to return, and we'll see this is going to set up kind of the end of the sequence, the one past the last, for when we go ahead and implement that end function within our binary search tree class definition. So let's go ahead and continue on. Now notice here, we're getting into some sort of while statement. While iter is not equal to the null pointer, we're going to push something to our stack, and that's going to be the address stored in iter. So our stack, and remember this is, let me make it lowercase here. Whoops. Stack, it's that data member, so our particular binary search tree iterator object owns that. So we're going to point, I'm just going to go ahead and put in, I don't know, let's do little circles or something to represent the nodes. This would actually be storing the address of the nodes, but this might be easier to visualize. So after we've done that, we'll go ahead and move our iter to iter's left. Okay, at this point, iter is still not equal to the null pointer. So we'll go ahead and push 8 onto our stack, and then we'll go ahead and move iter to iter's left. So at this point, iter is not equal to the null pointer. So we're going to go ahead and get into the body of our while statement again. We'll push back the address to this node to our stack, and then we'll go ahead and move iter to iter's left. And guess what? Iter's left is the null pointer. So at this point, our while statement's conditional is no longer satisfied. So we're no longer going to hit the body of that loop, and instead we'll pick up directly after it. So the first thing that we're going to do is assign iter to this location because it's currently here, and we're going to move it back one by taking the address off the stack. So just looking, what is the top value in the stack? This is the bottom. This is the top. The top value in the stack is the address of the node with the value 4. So iter is going to be assigned to that. And then we're going to go ahead and remove that element from the stack. So 4 will then be popped from the stack. And at this point, we're starting out good, right? We're at our in-order traversal starting from the right point. It's starting at the node with the lowest value within our binary search tree. And our stack kind of has a way to get back to its parent. And then also we have a means of getting back to 8's parent too. And we'll see how the stack's going to go up and down as we're performing this in-order traversal through our binary search tree. But this is the state after construction. So notice our two data members. We have a stack with 2 elements or 2 addresses, 2 node addresses contained within it. And then we have a node pointer pointing to the first element within our sequence. So it took that much setup to get to this point. And again, this whole stack, this is going to kind of be reminiscent of the call stack in the sense that it's preserving history. And since the object owns this, we're going to have access to that stack when we go ahead and implement our next element operator. To implement an in-order traversal for a binary search tree iterator, the constructor sets the iterator's initial position to the minimum value node of the binary search tree. We found this by walking from the root as far left as we could go, populating the stack along the way with the nodes we had encountered. The idea is that by pushing 2 and popping from the stack, we can move through the nodes forming the binary search tree in order. Therefore, the successor to the node that the iterator currently points should be at the top of the stack. And if we look at our implementation of the constructor to this point, we saw that first we found the minimum value node. We removed it. Its successor, 8, was then at the top of the stack, and our iter data member pointed to 4. The increment operator can then move to the next node in the sequence by removing the item residing at the top of the stack and assigning it to iter. And we'll see that in the next element operation video that follows. Looking at the algorithm in our constructor so far, we satisfactorily populate the stack when the minimum value node successor is its parents. However, keep in mind that the minimum value node can have a right subtree, indicating a node with a larger value than the current node, but one that is less than its parent. Therefore, you must visit that node next in our traversal, and our current implementation does not consider that. Therefore, we must make another check. If a right subtree exists to our current node that iter points to, the minimum value of that right subtree must get pushed to the top of the stack with the nodes we traverse to get to it occupying in order positions in the stack. In the updated version of the constructor, that we ensure that the stack is satisfactorily populated with the current node successor by removing first the minimum value node from the stack and assigning it to iter. And then what we go ahead and do is we check whether the minimum value node has a right subtree. If it does, we write an iterative statement to walk to the minimum value node of the right subtree, pushing each node encountered along that pathway to the stack. But you can see here that with this additional check that we will have after assigning iter to the minimum value node, we will check whether or not there is a right subtree. If so, we know the successor resides in that right subtree, and we go ahead and perform a walk down to the minimum value node of that subtree, pushing each node to the stack as we go. And we can see here that if we were to pop the stack, we would arrive at the next element in order traversal